The land of mathematics is an exotic and puzzling place. A strange language is spoken there, with talk of homeomorphisms, differentiable manifolds, and transfinite numbers. But also to be found there are magnificent landscapes, spellbinding ideas, and occasionally, even useful things. So let's take a whirlwind tour of the land of math. You just need a guide, that's me, and a functioning brain, that's you. We're not really going to do any math, just take a look at the countryside. Velocity is such a banal notion that we've almost forgotten that it is a mathematical idea. And yet, 3 or 4 centuries ago, velocity didn't yet exist. Or rather, it was very badly defined. Take ancient Greece, for example. At that time, mathematics was still a part of philosophy, and the world described by Greek philosophers was geometrical, perfect, and perfectly immobile. You could come across regular solids, absolute constants, and eternal truths. Movement wasn't yet on the scene. To the point that a certain Zeno of Elea, a philosopher of the 5th century BCE, invented a series of paradoxes which proved that movement was impossible. Take an arrow, Zeno tells us. Admittedly, we have the impression that it moves. But if we observe it at a precise instant, we can see that it occupies a perfectly defined position in space. Therefore, at that precise instant, it is immobile, as duration is made up of a succession of instants, and at each of them the arrow is static. We have to conclude that the arrow doesn't really move, and that movement is an illusion which takes place in the eye of the spectator. This paradox, over which philosophers of antiquity lost sleep, demonstrates that the notion of velocity shouldn't be taken for granted. Be careful, however. Quoting Zeno when contesting a speeding fine was still possible in the Middle Ages, but since the Renaissance, movement has surreptitiously slipped into the mathematical landscape. The idea which allowed this intrusion is known as infinitesimal calculus. And you already know one of the principal protagonists in this innovation, a certain Isaac Newton. Let me remind you at this point that an apple never landed on Newton's head. He simply explained how the vertical movement of an apple falling from a tree was a source of inspiration for his theory of gravitation. A student at Cambridge in the 1660s, Newton studied what was known at the time as natural philosophy, that is to say, mathematics, physics, earth and life sciences, and astronomy. He took a particular interest in the movement of planets and suspected that understanding the movement of an apple thrown into the air would be a first step towards understanding that of celestial bodies. But before understanding, it is necessary to describe how to make mathematical sense of this complex movement. To achieve this, he invented a new mathematical object, later to become known as a derivative. Let's look at this apple with a mathematical eye. We'll draw a graph associating each instant t to the height of the apple h. This principle allows us to trace out the trajectory and draw this nice parabola which represents the height of the apple in relation to time. To calculate velocity, we note its position at an instant t1, then at an instant t2. Velocity is the relationship between distance covered and time taken. It corresponds to the slope of the straight line linking the 2 points on the graph. If the line is horizontal, the velocity is 0. The more vertical it is, the greater the velocity. If t1 and t2 are at a distance from each other, we obtain the average velocity. But what we want to find is the velocity at a given moment. The more we reduce the distance between t1 and t2, the closer we get to this figure. But if the 2 points meet, velocity loses its meaning, as Zeno suggested. So it's a question of coming infinitely close to the instant without actually reaching it. What we obtain when we come infinitely close is the tangent of the curve, and the slope of this tangent represents velocity. Let's come back to our apple. The velocity is great at the beginning, the slope is steep, then regularly diminishes until it reaches 0, at which point it changes direction and becomes negative. Since we now know the velocity of the apple at each instant, we can draw the graph of it. It is maximal at the beginning, then regularly diminishes, passes zero at the moment when the trajectory of the apple reaches its summit, and then increases negatively, in fact, meaning that it continues to diminish. At this point, we realize that the curve of the velocity is simpler than that of the position. Position describes a parabola, velocity, a straight line. This is a derivative. If f is the function which describes the movement of the apple, we can associate it with a new function, f prime, which we call its derivative, and which measures the amount of change to f at each instant. And the extraordinary thing about the operation which we've just carried out is that it applies to apples and arrows, but also other things. We can calculate the derivative of all sorts of functions. And today, differential calculus has gate-crashed everywhere, from physics to economics via aeronautics and epidemiology. So to understand the movement of planets, Newton began with apples, and apples led him to invent a new domain in mathematics, later to become known as analysis. Thanks to him, science of the time had just taken a large step forward. Problem was that, apart from a few friends, no one knew about it. Newton waited more than 20 years before publishing his mathematical results, and when he ended up doing so in 1693, he discovered that someone else had already published more or less the same thing. This someone was Gottfried Wilhelm Leibniz, a German philosopher-mathematician who swapped correspondence with all the great savants of the time, in other words, a rival. The two men were locked in controversy for years. The English camp accused Leibniz of plagiarism, and the German camp looked upon Newton as a runner-up and bad loser. But the dispute also had a philosophical dimension. For Leibniz, celestial bodies move because they are caught up in an invisible but material current, while for Newton, the movement of planets and apples is the result of a mysterious distant force, gravitation, separate from the mechanical effects of the world of matter. Leibniz was in reality more materialistic than Newton, who, despite his revolutionary scientific ideas, kept one foot in the old world. This was apparent in his passion for alchemy, into which he plunged headlong for a large part of his life without any notable results. In brief, differential calculus has two putative fathers, to whom one would need to add a whole gallery of portraits to be totally fair to everyone, something for which we don't have time because let's not forget that our subject is velocity. So thanks to derivatives, we can calculate the velocity of apples, arrows, and sports cars, but also the yield of our savings account, the propagation rate of an epidemic, and how quickly our coffee gets cold. All that thanks to a piece of fruit and a pair of putative parents. Talking of apples, let's come back to our curves. From that of position, we extracted that of velocity. But after all, why stop there? Why not extract the derivative of the derivative? That will give us what is known as a second derivative. Let's try. The curve of velocity is a straight line, so its tangent follows the same line as the curve, and the slope of this tangent is always the same. So here's the curve which represents the derivative of velocity over time. It's a straight horizontal line which corresponds to a constant. But the derivative of philosophy has a name in everyday language: acceleration. The complex movement of an apple actually results in the constant acceleration to which all terrestrial objects are submitted, gravitation, which Newton was to bring to light over the following years. That's the magic of derivation. Behind the complexity of reality, it allows us to discover hidden regularities. Behind the agitation of objects and trajectories, it displays the Earth's unchanging gravitation. In a certain way, Zeno of Elea was right. If you look carefully, behind movement is the immutable.